The title of my talk is Using Maple to Investigate Integer Length Preserving Directions. I will explain what this means. I have used Maple a lot for computations, for exploration, and also for graphing. This is an overview of the talk. This work was motivated by a webinar given in 2015 by Robert Lopez on linear algebra, how to find eigenvalues and eigenvectors, we call them eigenpairs, for a matrix A. The talk had to do mostly with 2x2 matrices. At the end of the talk, Dr. Lopez posed this interesting question. For an eigenvector, the matrix preserves the direction, but not necessarily the magnitude, the norm of the vector. What about the dual question? What about vectors for which the norm is preserved, but not necessarily the magnitude? So Dr. Lopez was looking for an example of a matrix with integer entries for which these directions would be integer also. And he came up with this very nice example by doing some a for loop in Maple. This matrix has two vectors with integer coordinates, 1, -1, and 17, -19, such that when you apply the matrix A, you get vectors that have the same length, but no longer the same direction. You can think of, we are going to also identify A with the corresponding linear map from the plane to itself. So for example, if you grab the second vector, the norm is the square root of 650. When you compute the image of this vector under the map A, you get a vector that has different components, 11 and 23, but they have exactly the same norm. So for this particular matrix, the eigenvectors are also integers. These vectors, the map preserves the direction, but not the norm. So as I said, this question is in a sense a dual of the other question. Now, the same as for eigenvectors, if you have a vector for which the norm is preserved, any multiple of that vector will have the same property. So you have an entire line with this property that I'm going to call norm preserving lines or norm preserving directions. So the goal of this work is to actually find matrices for which the norm preserving directions can be expressed using integer vectors. So for the 2x2 cases, I ended up finding entire families that have this property. For the 3x3 cases, so far I only discussed a couple of examples to see what one would expect. So let's say general considerations. If a matrix has an eigenvalue 1 or -1, then the corresponding eigen line is also a norm preserving line. And in the extreme case, when A is an orthogonal matrix, all directions are preserved. Think typically of a rotation. Then all the norms are preserved, but the directions are almost never preserved. Now, in this case, you will have that all vectors, all norm-preserving lines are rotated by the same angle. In the general case, this does not happen. So I consider a general matrix with integer well, first consider general entries A, B, C, D, and ask the question, when do we have vectors V with components x, y, such that the norm of V, the usual Euclidean norm, is the same as the norm of its image AV. When you write down the square of the norm and use the usual dot product, you will see that the square of this norm depends on the symmetric matrix B, which is A transpose times A. And the corresponding equation for these vectors is given by this, which you can consider a quadratic form. Now, if we write down the explicit entries of the matrix B, here I call them M, P, and N for short. You can see that M, P, and N are homogeneous polynomials of degree 2 in A, B, C, and D. So the corresponding quadratic form is written here, and these norm-preserving vectors will be solutions of the equation phi of xy equals 0. Now, when do we have solutions in general? Not necessarily for integer matrices. We get this condition: the sum of the squares of the entries of D of A cannot be smaller than 1 plus the square of the determinant of A. I wouldn't want to get into the details of the proof, which is not hard to do, but I want to just point out that geometrically, these results comes from the following fact. If you call lambda 1 and lambda 2 the eigenvalues of the symmetric matrix B and order them, then the extreme properties of the eigenvalues tells us that the smallest eigenvalue is the minimum of the values of the dot product V with BV for unit vectors, and lambda 2 is the maximum. And therefore, we will have solutions only if the number 1 is between these two values. Geometrically, if the eigenvalues are not 0, if they are strictly positive, then V comma BV, the dot product is an ellipse, and the half axes are given by 1 over the square roots of the eigenvalues. And we will have solutions only if the corresponding ellipse intersects the unit circle. Here is the picture for the matrix in the example by Robert Lopez. Since the non-preserving directions are very close, you get an ellipse that intersects the unit circle at close points. Now, when you assume that the entries of the matrix are integers, then the corresponding quadratic form has integer coefficients. Remember that M, N, and P are our homogeneous polynomials in A, B, C, and D. The question is to solve this Diophantine equation. So in general, I found that there are 4 families of matrices that have this form. We have 4 choices of pluses and minuses, and they are transposes. They have this nice property that the non-preserving directions are generated by integer vectors. The matrix by Robert Lopez was one of the families. It's A minus 1, C minus 1 for specific values of A and C. In general, for matrices like this, the solution lines are generated by one of the vectors is always 1, -1, and the other one has this longish expression on the coefficients of A. So here is another example. If A is 2 and C is -3, you get the matrix 2, 1, -3, -4, for which the norm-preserving lines, I call them solutions line also, are 1, -1, and 4, -3. Here is a corresponding picture. You have the two lines, as you would expect. They pass through the intersections of the ellipse given by AV in norm equals 1, and the unit circle. Okay, so what about the 3 by 3 case? It's much more complicated. It's also much more interesting. You can set up the same equations, assuming that A now is a 3 by 3 matrix. You get the square of the norm of B is a quadratic form generated by the vector, by the matrix B, which again is symmetric, is A transpose A. You get the same equation, but only now for a vector V having 3 components, X, Y, and Z. Geometrically, you get the same condition. There is a solution if and only if the number 1 is between the smallest eigenvalue of B and the largest. Otherwise, there are no norm-preserving directions. Now, this equation is now an ellipsoid in general, and the corresponding equation equated to 0, what I call here equation 9, is a cone, right? So the corresponding picture now in 3 dimensions is you have an ellipsoid intersecting the unit sphere, and the cone passes through the intersection of this ellipsoid with the sphere. So let's consider some examples to see what one would expect. The first example is this symmetric matrix. I assume that I can have either integer or rational coefficients. So the corresponding B, which is A transpose A, in this case is the square of A, is the matrix here, and the corresponding equation for the cone is this one. And this equation has infinitely many real-valued solutions. Now, what about integer solutions? It turns out that the equation has no integer solutions, non-trivial. It all has to do with the result that I highlighted here. The quantity inside the square root has to be a perfect square. So you get a Diophantine equation, and you can prove that this equation has no integer solutions. Okay, so this is an example where you have no solutions. In the other end of the spectrum, we have an example that has a dense set of solutions. So this is again a symmetric matrix. We again compute B, and it turns out that in this case, the corresponding cone is degenerate. It's a plane. So the corresponding picture is this one. The plane intersects the ellipsoid, which in this case, it's tangent to the unit sphere. And the entire plane consists of solutions. So all you have to do is pick a couple of, vectors in this plane that generate the plane and have integer coordinates. For example, here I pick 1, 0, -1, and 0, 1, -1. Any combination with integer coefficients will generate a solution vector in this plane. The last example is a sort of in between. There are infinitely many solutions lines, but they are not necessarily dense. This matrix is no longer symmetric, but when we write the corresponding symmetric matrix B and the Diophantine equation for the cone, and when we try to solve, we get this interesting result. First of all, there is one solution line, negative 1, 1, 0, that corresponds to an eigenvalue in absolute value equal to 1, and all the other non-zeros, all the other solutions in general are given by this parametric expression where V and R are arbitrary integers. So here I highlighted a couple of cases when V and R are correspondingly equal to 1 and 4, you get two such vectors. And for another choice of V and R, you get another two. So of course, the 3x3 case is wide open here. Thank you for your attention. These are some references. This is the summary of the talk, if there are any questions.